tagadan 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 pam pam tagadan 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 pam pam tagadan 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 pam pam tagadan tagadan pam pam tagadan 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 pam pam.
All right, up next we have DK Panda from Ohio State University talking about high performance and scalable middleware. DK, welcome again to the Swiss conference.
Yeah, thank you, Brian and everybody, Gilad, Hussein. It's a great pleasure again to see all of you, and I think I've been coming here since the third one or the second one, I don't remember. Every year I come and try to share some of the latest things, what we have been doing. So today I'll be, actually at this conference this year, I'll be wearing two hats. So today I'm wearing the OSU, the Ohio State University hat. We also have a commercial spin-off called Xscale Solutions, which is the sponsor of this conference. We have a booth there on the other side of the room. So I'll be wearing that hat tomorrow for another talk where we'll be going into more details of some of the commercial offerings, what we have on top of what we provide from the OSU side. And during the break times and all, I'll be there, and please feel free to stop by and then talk with me more about that. And since we have a little bit more time, and it is actually 4 o'clock in the morning in East Coast, so please feel free to ask me questions, okay, so that I remain awake. That is the most important thing, okay? So today I'll be talking about this title is High Performance and Scalable Middleware for HPC, AI, and Data Science. So I'll take a very global look at where the field is going, and I'll try to provide solutions to different phases. So if you take a broad look in the past, like starting from like a 1975, almost like a 45 years back, we had, of course, the traditional scientific computing, or the HPC. Then around 2000, the big data analytics came. Like people had a lot of data, then the challenges were how we can combine HPC and big data. And of course, around 13 years back, we got introduced to the field of AI, the machine learning and deep learning, and of course that has changed the way we have been making progress in the last 13 years. But then what is happening, there is a newer kind of things coming up, which is called like a computing continuum, okay? So this is the left-hand side. Many of us are very familiar with this. We have the scientific computing, big data, and artificial intelligence, and we try to run these applications on traditional HPC systems or on the cloud. But if you take a look at the right-hand side, if you take a look at a lot of data are being generated by edge devices. Okay, these edge devices could be something from the field, something from medical instrument, something could be a telescope, or anywhere. The data is coming from very different places, and then we need to operate on those, and all the results also need to be going back to some of these devices or people working with those devices. Okay, so this is what we call like a computing continuum. So this is the new field which has been emerging. Many people have been talking about this. Now the question are, not only the data is being generated, how do I do the computation? Should I be doing it at the edge, or should I be doing it at the cloud, or should I be doing it at the HPC, or a combination of all these things? Because we want to provide the appropriate solutions to these problems. So let's take an example of digital agriculture. I know like the world, the population is increasing. Every country you go, there's a lot of demand on how we can produce crops with the lowest cost. Okay? Traditionally, like if you take a look at this example of a traditional farmer, might be the farmer, let's say there is a crop and some disease has happened. Of course, the farmers have some knowledge. They go and then spray the pesticides. But as you might be knowing, let's say you have a garden or even a smaller scale version of the farm, not that every part of the field has the same disease. Okay, in a garden might be this part of the thing has got disease 1, disease 2, disease 3 kind of things. Now the question is, can I bring AI here? Okay, so can I like fly a drone, and then the drone automatically flies over the field, one or more of these drones, and in real time, it can actually compare the photos taken by the drone with the ML models of that crop and then try to exactly find out what kind of diseases are there or which part of the field has what kind of disease. And then the question is, can we actually take that information and actually feed it back to the sprayers or the tractors so that it actually goes and sprays the appropriate amount of pesticides at each place. And if we can come up with this kind of a solution, you'll be seeing that not only the cost reduces, but it also helps the earth, that we are not polluting it anymore. It helps climate change and all those things. So this is where my last 30 minutes, actually, I'll be talking a lot on these kind of applications. We got funded a new NSF AI Institute from National Science Foundation in US to really take all these HPC, AI, and big data analytics to these kind of applications or the domains. So I'll be talking about that a little bit more. But just hold on for the second part of the talk. So, and this is, I just gave only one example, but the same examples actually hold good depending on your discipline: smart cities, smart food sets, smart manufacturing. So every field is actually moving to the next stage. Okay, transportation, surveillance, animal ecology, or computational medicine. Any of these fields you see, lots of sensors, lots of data are coming, and then you need to operate on those data in an intelligent manner, and then give it feedback to the end users. So now with that kind of a very broad objectives, now let's see how we are designing the HPC systems. Okay, so this is very much familiar to most of us. Like we have all these modern HPC clusters are being very heterogeneous. We have starting from multi-core, many-core processors, high-performance interconnects like InfiniBand or DPU, Slingshot, all different kinds of networks. We have accelerators, FPGAs, and of course we have SSDs. And these kind of devices are not only there on the on-premise systems, they're also on the cloud. So you can take a look at all the different clouds. These are all over the top 500 systems. So now if I take this kind of hardware and ask the question, how do we design the high-performance and scalable middleware for these systems? And especially keeping that computing continuum in mind. And for all these stages, 1 to 4, I indicated. And while taking advantage of all these heterogeneous resources, we have CPU, GPU, DPU/IPU, or whatever people are calling XPU, but for both, including HPC, traditional HPC, and cloud resources. So that is the kind of I'll try to provide answers to these questions. So I'll first start with the first stage 1, 2, 3, and then I'll come back to the stage 4, the computing continuum, a little bit later. So here, if you take a look at these, even though these fields started at different period of time, these days, any common workflow actually has many of these components. So any complicated workflow, you might be trying to, let's say, operate on some part of the, some stages or some parts, and then bring your big data analytics or even AI-driven, which is being embedded. So all these things are being coexistent. And this is where I'll try to say, or try to show, how you can design the middleware, and especially here I'll be trying to show how you can design MPI-driven middleware. Okay? Not only trying to help HPC, but also machine learning, also big data. I'll show examples, like you can run Spark on MPI. Okay? And as long as the MPI library is available for any cluster, which is mostly common anytime a new networking technology comes, MPI library is the first one to come. And if that is already available, you can actually run Spark. You can run Dask. You can run machine learning, deep learning, everything. I'm trying to take the denominator to the MPI library. And as long as you can design a very high-performance, scalable MPI library, you should be able to handle all these things. And this is where I'd like to say, this will be like a conversed software stack or a middleware for the next generation systems. So with that kind of a background, I'll start with the MapRich MPI library project. Many of you might be familiar. If not, I'll try to introduce that. Then I'll go into the high-performance deep learning, machine learning project, and high-performance big data project. So these are the traditional projects, 3 projects in my group we have been carrying out for many years. And then this is the project which we started last year. This is the NSF AI Institute called Icicle. And that actually tries to take all these HPC, big data, and AI to the computing continuum. Okay, and that's what I'll be talking. There's a very nice website. There is also a nice video. I'll play it here. If you're interested, just go to icicle.ai. Okay, and then you will find out a lot of information there. So let me start with this converged middleware. The first, of course, is the HPC. That's traditionally it has been there for, let's say, MPI, PGAS. So this is where our MHP library comes in. If you are not familiar with this project, we started this project almost day one of InfiniBand. Many of you in the room must be familiar. Go back, InfiniBand was introduced in October 2000. Okay, almost like 23 years back. And prior to that, if some of you old-timers are here, you might be knowing like we had Merinet, Quadrix, those were the kind of the interconnects which were being used. As soon as InfiniBand came, my group was the very first one in the world to really jump in and have a high-performance MPI library using that InfiniBand. And we had the first demo at the Supercomputing 2002. And I still remember that it was in Baltimore. At that time, InfiniBand technology was just coming up, and it was very hard to even have an 8-node running on a stable manner. Okay, but things have improved quite a lot. I mean, these days, multiple thousands of nodes are being deployed with InfiniBand. We have been on that ecosystem for the last 22 years. I'm very proud of my team. And not only we started with InfiniBand, but nowadays we provide the MHP library, provide supports for Ethernet, iWarp, for RDM over conversion enhanced Ethernet RoCE, Omnipath, even AWS EFA, Elastic Fabric Adapter. We have a native design for that. I'll talk a little bit about that tomorrow. And also the Broadcom RoCE and Rockport networks, Intel Ethernet, and very latest, we also support the Slingshot. From the craze. So we cover all the interconnects, and I'll try to show some performance numbers. And at the same time, also we do for all the accelerators, NVIDIA, AMD GPUs, Intel GPUs is just coming. We just had a publication accepted, which will be presented at CC Grid, so we'll provide support for also the Intel GPU. So currently we have more than 3,300 organizations. These are registered organizations with our website in 90 countries using the stack. And just from our website, we crossed 1.66 million downloads just from our website. Okay. Of course, our stack is a part of Red Hat, SUSE, OpenHPC, SPAC. You can also go through those and then install these. We don't keep track of those. And not only is just the numbers, but we have been empowering in this field for a lot of top 500 clusters using our libraries over the years. So this is the kind of the broad software architecture for our library. Here we have like all the left-hand side bottom, we have all the networking technologies, starting from InfiniBand to up to going to the Slingshot. This is where we have all the accelerators, including actually DPU. I'll show a little bit numbers on the DPU today, but tomorrow I'll go into more details of the DPU. That's MHP to DPU libraries being developed by this commercial spin-off, which is the Xcal Solutions. If some of you are in the mailing list, we made a release just yesterday. I'll show you very fresh numbers in today's talk. And then we have this the middle part, which is our high-performance communication runtime. And in the top, we provide support for not only the MPI, but we also provide support for the PGAS, MPI plus PGAS, that's the hybrid MPI PGAS. And once we have that support, then not only we try to satisfy the HPC jobs, we also have built like a DL, ML on top of that, as well as the Spark, data science, and those will be the solutions which I'll be talking. And of course, I mean, since we are, like here I'm giving the talk from the issue side, I mean, of course, our primary objective is for publications. Anytime some new technology comes, we jump in. Those are the kind of the initial papers we have. But then once we have these papers, in 6 to 9 months, we actually take these solutions and then push it into our MRPH and all other libraries. We do very rigorous testing and then try to push it to the public uses. So those of you who are familiar with MHP, we had the 2.3 series, which have been going for long. And last year, we started this new series, which is the 3.0 series. You will be seeing, we had this release last year before SC and before we do an MHP user group conference. So here, basically, like, we have our own design, and now also we have added the support for UCX and OFI. Because some of the network vendors are not exposing their lowest level, and they are exposing it through OFI or UCX. So we have actually brought that design so that now you have a lot of choices. Okay, so we should be able to run MRAPIS2 on any of these networks, and in addition, you will also have support for the native design. Whichever network is exposing the lowest layer, let's say InfiniBand or Rocky, we go to the lower layer. But if you think of like a Slingshot, they only allow up through OFI. So we can't do anything but build on top of that. Okay. Same thing is also kernel-less network. So this is where being provided through OFI. So we support that through OFI. Okay. So you can think of it like a mix and match kind of objectives we have taken, so that you should be able to utilize MRAPIS for all the platforms. So let's take a look at some of the sample numbers just to get a feeling. So this is like our 2.3 series numbers. If you take a look at the AMD Milan with SDR200, one of the very latest configurations. So here you will see like a intra-node point to point. Here you will see almost like 190 nanoseconds we can actually give core to core. Within the intra-socket, that's the kind of the latency. And then on the inter-node side, this is the SDR200 with AMD. So we get around like a 1.9 microsecond. And of course, the right-hand sides are the bandwidth. We will try to saturate the network. These are some numbers on the Slingshot 11. That is actually the very latest network, which is widely used, also used in the Frontier, which is the #1 system. And I believe in Switzerland, CSCS and other places also have some of the Slingshot machines. So here we get around like, if you use our very latest version, you can get around like a 2 microsecond internode. Node to node, you get this, and bandwidth wise, you get around like a 24 gigabytes, or bidirectional you get around 42 gigabytes. Okay, so that is the very kind of the latest what we see on the CPU side we can get. Of course, we have numbers for all the other interconnects, but due to lack of time, I'm not going over those. Our MRAPIS website has also a lot of performance numbers. Please feel free to take a look. Now that is purely on the CPU side. Of course, on the GPU side, as you know, there is a lot of advances taking place. I just want to ask a question. How many of you heard of this CUDA-aware MPI, the terminology, okay? Several of you. Very nice. So in fact, this was introduced. This term we actually introduced in 2011. At ISC conference, we had a collaboration going on between OSU and Mellanox. That time it was a separate company, and NVIDIA. So they have this GPU Direct RDMA came that during that time. So the broad idea was that if, let's say on the right-hand side, we have the GPU here and then InfiniBand adapter, most of the time, if you are an application programmer, you of course submit a kernel to the GPU to do the execution. But if I want to move the data, then you try to do a CUDA mem copy, then do an MPI send. On this side, you do an MPI receive, and then you do another CUDA mem copy. Okay, that is the kind of the traditional approach many users use. But then if you do these things, and you have several steps of copying, and especially if the message size is very large, you don't get very good performance. Okay, of course you can do some pipelining, but then the application people, let's say you are an astronomer or you are a neuroscientist, instead of focusing on your science, you are actually trying to see, okay, what should be my GPU pipelining, how I should be optimizing CUDA. So they spend more time on computer science, not on their science. So to help them, we actually that time came up with this concept. The CUDA-aware MPI library came. So the idea was that if I have a data from the GPU, can I actually directly say that, okay, do an MPI send from that GPU buffer? Okay, instead of saying it's a host buffer, I say GPU buffer on the send side, and on the receive side, I say the similar MPI receive. That's all. Okay, so you launch a kernel, then you said MPI send, other side you do MPI receive, followed by your computation. That's all an application scientist need to do. Then the MPI library actually performs all kinds of optimizations. There are so many different paths. How do you move the data, as you saw in the animation? And MPI library will try to give you the best performing path, okay? And if I can achieve that, then the end user, like as I said, the astronomer or neuroscientist or a chemical engineer, they don't have to really spend time on understanding what is happening below the system, and they can focus on their science, and that will lead to high performance and high productivity. Okay, so that was almost like 12 years back. We introduced this concept, and then we showed these numbers, and these numbers have remained more or less stable over the years. You can see like the T line is without using this CUDA aware, and then if you use the CUDA aware, see the number 1.85 microsecond. Okay, I can actually send data from a GPU from one node to a GPU of another node, not on the same node. Okay, using this, of course, there are other libraries. We work together with NVIDIA to have GDR copy. There is another library also used. So GDR copy and GPU direct RDMA, you put both these together, and a library like MAP is 2, and you will get this kind of numbers. Okay, and so now you can see like you get almost like a factor of 10 improvement in latency, bandwidth and bidirectional bandwidth. You get almost factor of 9 and 11, and that really boosts the application performance. Okay, and that's what actually is continued over a lot of years now. If you see all other MPI library, a lot of even you talk about like a Nickel library, TensorFlow, PyTorch, a lot of these libraries are actually been moved into that CUDA-aware MPI concept. Okay, and that is actually giving a lot of boost into the application performance. So that design has been going on. Now, since last 2 years, we've started this new thing called on-the-fly compression. Okay, so if you think of like a modern GPUs, like you think of like a A100, okay, there are so many cores there. Of course, that is helping us with the computation, but when I try to do the communication, those cores are sitting idle. Okay, so what we started the concept that if let's say I have a very large message to send, even in the context of the CUDA-aware MPI, can I actually do compression on the sender side on the fly, and then send it, and in the other end I do a on compression on the fly, and let's say if I can, the compression is good, and I can reduce, let's say, the message size by some factor, let's say 4, 5, 8, 10, then my overall latency will reduce. Okay, even including for the overhead of the compression and on-compression. Okay, and that is the kind of direction what we have been focusing for the last several years. This actually we introduced in 2021 at IPDPS. It got a Best Paper Finalist award there. Now, of course, the question is, can this compression? There are a lot of compression algorithms which are there, like a lossless compression versus lossy compression. There are a lot of choices, and that field also is still evolving. But the idea is that, or the challenge is that, whether the application still maintains the accuracy or not. Okay, like we don't want the application results to be changed, okay, by changing this compression. And here we are showing, especially in this paper, we worked with this application, which is a earthquake simulation application called AWP ODC, designed by San Diego Supercomputer Center and USC. So we actually worked together, and these are some of the results, and even including the compression, we are able to see on the left-hand side, we are able to improve the throughput by like 18%, 35% without affecting the accuracy. Okay, so just using this on-the-fly compression, we're able to boost the performance. And in the right-hand side is the time per time step. As you can see, like we reduced by 15 to 16%. So that is actually a point-to-point. This is already available in our library. If you have an application, you want to play around with it, please feel free to do that. Now, that is actually a point-to-point. We started with the point-to-point design. But then, as you know, especially in the HPC domain, there's a lot of focus on collectives. Okay, collectives like all reduce, all to all, those kind of things. But now, in all these collectives, there are a lot of communication steps happen. Like I send it to you, you combine, and then you send it back to me or to somebody else. Of course, you can build that on top of point-to-point. But then, if the compression is happening in every step, there's a lot of overhead. Okay, so we rethought that, okay, can we take the compression to the collective level, okay, so that you don't do a point-to-point kind of mechanisms, and this is what we presented last year at ISC, and here you can see the left-hand side, it's actually all-to-all. It's a scientific simulation, which is a PSDNS, and we are able to improve the execution time by almost 29%. While maintaining accuracy. Okay, so that is the first thing. We don't want to disturb the overall execution of the application or the accuracy or the results, but we are trying to enhance the runtime to make it faster. And then the right-hand side is actually an AI application. Some of you might be knowing like a deep speed. That is kind of a middleware which gets used, all the recommendation models and all, trying to use this all-to-all. And similar kind of things here we have done is like we are able to reduce by almost 36%. Okay, so these are again, as I said, like this is the very latest version. Our MAP is to GDR 237. It has built-in compression. There are parameters you can actually activate the compression and see if you are able to accelerate your application with this compression. Okay, now Hussein, that is a very great question. So what is Hussein is asking from an application perspective, do we need anything first of all? And then second is, okay, how much benefits we see, okay? So the first of all, this is application transparent, okay? So we are not expecting any input from the application. Just like any API library, as you know, you run it with some runtime parameters. So that's all. You specify saying whether you are turning the compression on or not. But then the second question is, do I see the benefit or not? Okay. So that depends. So here if you see like there are all this compression, there are different rates. And in a typical application, again, let's say there are so many communications are happening, might be some stages, depending on what data you are sending, your compression benefit may be there or may not be there. It is application dependent, right? So based on that compression algorithms, if I get the compression in most of the stages, then I'll see the overall benefit, okay? But it might be in 10 stages I got the benefit, another 5 stages I didn't get the benefit, so then might be the benefit will be a little bit lower. So that's why you see all these different experiments, different system sizes, like let's say 32, 64, 128. We see varying performance. Same thing also happens here with a different compression. So broadly, what we can do is like we can work with you people for your application, and let's run it with the different like these parameters. Either you can do it or we can work with you to see whether you are really getting the benefits or not. Okay? It will be dependent on the data dependent, because we are like library, we are just providing the support, and it may help or may not help. So I'm trying to show some scenarios where it is helping. Okay? But might be there will be some application, depending on the data you are sending, it doesn't have, irrespective of like how much compression I do, the actual data size doesn't reduce, or it reduces only by a few percentage, then it'll backfire. Does that answer your question? Okay. Any other questions from anybody until this time? Yes?
Thank you. Good? Yeah. Just would say that maybe it depends on the size of the buffer you would like to communicate, and do you have performance according to the size of the buffer or something like that? Maybe it will give more details, and if your application will gain something or not, depending on the size of the buffer you want to communicate.
Yeah. So if you please take a look at the paper, I can also talk with offline. So what we did is, first of all, I am showing the end results, but for all these schemes, actually you can actually run some few experiments, okay, with these different compression mechanisms, and you can see whether your data size is being compressed or not for your application and for your configuration, okay? And then based on that, then you will see whether you are gaining it in the overall performance or not, okay? So you should be able to carry a lot of these experiments yourself and see whether, because at the lower level, if I don't get the benefits, then upper level I don't expect, all right? Any other questions from anybody? At least some people are awake, okay? So good. So then I talked about a lot about the NVIDIA GPUs. We also have the similar support for the AMD GPUs because many of these newer systems are coming. And there, if you see, it's like we have done the ROCm aware design. That is the ROCm is the library from NVIDIA. And here we have done a very tight integration again in our MHP2 GDR library, so it will run transparently whether you have AMD or NVIDIA. And here, especially if you see, even I'll show even some more results later on. Sometimes our collectives and all, how we have optimized designing using this the GPU direct RDM and all, we can give you even far better performance than what the RICL provides. The RICL is the equivalent of like a NICL, which is the collective NVIDIA collective library. RICL is the AMD library. So compared to that, we give far better performance. So this is actually this release is coming out next week. I'm just trying to show some preview. This is in our MHP Plus series. So the MHP Plus series actually, if those of you are familiar, we had 3 different versions actually. There was a base version, there was an MHP2X, which is an advanced version, there was a MHP2 GDR, which is a GPU direct RDM version. So we have taken that MHP2X and MHP2 GDR combined, so that is our plus version. So moving forward, later this year, you will see there is a base version and a plus version, okay? And this is a plus version, which we have again made an alpha release earlier. This will be the beta release, which is coming out. So here again, you can see the same things. Let's say these are like the collectives, MPI reduce. Look at the numbers, the RICL, whatever AMD provides versus what we provide, our numbers are far better than RICL because we are trying to actually utilize all the GPU direct RDMA principles in optimizing our collectives. So next, let me just show you this DPU. How many of you have heard of DPU technology? Data center processing unit? Some of you, okay, good. I know Gilad has a complete talk tomorrow to introduce you that. So this is the kind of the next generation adapters NVIDIA / Mellanox is pushing, where not only the adapter has the basic RDMA concepts, but now these devices have several programmable cores. Okay, so I call it like a just like the regular organization. We have executives and assistants. So just like 5 executives might have several assistants, so same thing is happening to the HPC environment. So the Bluefield 2, which is one of the DPUs, it has 8 programmable ARM cores. And the Bluefield 3, which has just been announced, has 16 ARM cores. So think of just like an executive, you offload some of the tasks to the assistants. Okay, so can we actually try to bring that concept into our HPC? And here I'll show you some of the things what we have done: offloaded NPI non-blocking collectives. And this is the product which is out. We just announced it yesterday, the latest version. And this is from the Scalable Solutions, and I'll go into much more details tomorrow. So it has actually non-blocking all-to-all. So all-to-all, is a very complex operation. Any application using all-to-all takes a lot of time. MPI 3.1 standard introduced to do it in a non-blocking manner. So that means you can actually introduce all-to-all or invoke all-to-all, but while all-to-all is going on over the network, you can actually do some computation. Okay? And I give this very simple example which can relate to a lot of people. I mean, think of like a Friday evening. If your friend is coming or for a dinner, you decide saying, oh, we want to go for a movie, okay? So then the question is, okay, while your friend is coming to your home, do you sit idle and just keep on waiting for your friend to come, or you do some tasks, whether it is cooking or cleaning or getting ready for tomorrow, okay? What do? Is it the former or the later? Do you just sit idle and wait for your friend to come? Yes or no? We don't do that, am I right? We human beings are so busy, always we have so many things to take care, am I right? We try to achieve. So that is the difference between blocking and non-blocking. So in the blocking mode, you don't do anything, just sit idle there, okay? That means you are not overlapping computation with your communication of your friend. On the other hand, if it is non-blocking, that while your friend is coming, you are actually working on your own things. And then your friend comes and then you combine. So that is the whole idea we are trying to take, this MPI library concept. Now you can take it to all this new DPU technology, DPU, IPU, XPU, and all those things. So here what we are trying to show, an I all-to-all. That means there are two versions here. The red one is MFPs 2, which is not providing very good support for the non-blocking, whereas this MFPs 2 DPU, where since these ARM cores are there, you can actually tell them they're your assistants. So you tell them, okay, continue with the all-to-all, and then the processors can keep on doing the computation. Yes? Hold on to tomorrow. I'll go into all these details, okay? Tomorrow's talk, okay? So here if you see, these are very fresh numbers, by the way, okay? Just taken last week. So here you see, even depending on your message size, this is a 32 node, 32 ppn, like 1,000 process run. You can see the almost 84% benefits I can have. Okay, I have offloaded, so my CPU cycles are free, and then what we are trying to show here, it is the total execution time, compute plus communication, not just communication. Okay, and this is a part of the OISU micro benchmarks. If some of you are familiar, we have been doing that project even from year 2000. It has actually all these things. You just run these and take the measurement. So we are using standard OME benchmarks. We are not doing anything else. So now the question is, this is only all to all, but now let's see the application. So this is an application we have been working called P3D-FFT. So FFT, as you know, has an all-to-all. So this is a version P3D-FFT. So this is actually, of course, application you need to modify. Okay? So that is another thing we need to keep. Just look at my movie example, going to the movie. We human beings also have to modify our workflow. Okay? If you just sit idle there while your friend is coming to go to a movie, then you don't see any benefits. So we have to have some work. So that is the whole idea, that the application may need to make some changes, that you try to initiate the all-to-all or any other collectives, but you still, while that going on, you still have some computations to do. If we can achieve like that, and a lot of applications have those kind of things which can exploit, and here especially if you see this is the same, this is a 1,000 process run, and of course this is a P3D-FFT, you can actually allocate different grid sizes. So this is a 32 by 32 process grid, and different grid sizes like a 1K by 1K to up to 2K by 2K by 4K, you see 24% benefit at the P3D-FFT level. Okay, so if you have a P3D-FFT in your overall application, depending on how many times you invoke that and all, you will see this benefit. So that's what we are trying to actually push, the MPI library, and tomorrow I'll actually try to show even computation also you can offload. Okay, this is a part of the MPI library, but think of like these ARM cores, they're not very powerful. It's just like assistants, you know, they may not be, I tell this to all my students. Think of like if you hire a PhD level assistant, what can you offload? Think of like a normal world. Everything, all right? You tell your assistant saying, go write a proposal, get the grant, carry out all the papers, the experiments, write the paper, just put my name there, all right? But then those will be very expensive assistants, okay? So typically you have assistants like with reasonable kind of a degree, and then either high school or college, depending on their capability, you try to offload. So that's what is happening in the field. Depending on how much capability that adapter has, we can try to see how much we can offload, okay? But more will be there in tomorrow's talk, okay? So like this in the MFPs part, I mean, I'm trying to put together like almost 20 years of work here, and then let's see the end benefits. So these are some of the testimonials from other places, like these are the Oak Ridge Summit. People have been using our library together, other libraries, and see MFPs performs very well. Idaho National Labs in US, they do a lot of nuclear energy research. So not only they have MPI, but they are also using like a Moose, PETC, a lot of those modules. And they actually showed these very interesting numbers last year at the MFPs User Group Conference. This was their statistics on 2021. As you can see, their users were using MFPs, OpenMPI, Intel MPI on different manner. But see the left-hand side. In 2022, all their users have moved to MFPs. So we work very closely with them trying to optimize the libraries on their platform so that their users are actually getting the best performance. Now, the next two slides are very interesting. These are like some of you must have heard of these. This is the NASA's DART mission. How many of you heard of this? Like the last year? So I'm very proud that we actually are part of that team. In an indirect manner, we have been working very closely with Lawrence Livermore National Lab. This is where a lot of these things happened over the last 13 years. So they have been using our library MFS2 on all their machines to really build this mission and make sure that it works. And also, this is also, I'm very proud that we contributed to this nuclear fusion research. How many of you have heard of this? Many of you are, right? So this again came from the Lawrence Livermore, so we work with them very closely, and I'll go into a little bit that also in tomorrow's talk. We have been working with them not only across the systems for given application. We have application, we do that through Excel solutions. If they have any critical application, we really go and optimize that. You know, any MPI library has almost 100 to 200 parameters, okay? You can actually try to optimize so that your application really runs in the most optimized manner on a given system. So those are the MLP side. Let's move to the machine learning, deep learning. So here what we have done is, as I said, since MPI library is optimized for a lot of the systems, can we take advantage of for other domains? So here what we have done, I'm sure many of you must have used TensorFlow, PyTorch, etc. Now, there is a library called Horoword. There are intermediate things are also middleware called Torch, distributed, deep speed, and all these are coming. So what we have done, these middlewares actually, they have different APIs, okay? So especially, let's say Horoword or Torch, distributed, deep speed, they have an MPI API. So what we have done is, we have actually linked our MVAPIS library through those APIs. Okay. So, and this is a project we are continuing called high performance deep learning. And so the idea here is that as an end user, let's say you are an AI user running TensorFlow or PyTorch your application, you don't have to change anything. Okay. It's the system administrator or some intermediate version needs to be modified. We have a very detailed guideline. You can actually download TensorFlow, PyTorch, Horoword, our library. You can actually build it in a few hours. Okay, and if you don't want to do, actually we have an Xscale AI package from the Xscale solution side. I'll go into more details. That actually you can just download and install and it runs. Okay, and in that way, what we can do is actually all the MPI level performance I can push it up. Okay, so we are all now AI applications, whether machine learning, deep learning runs much more faster. Let me show you some sample numbers here. The first one is, as you know, these days all these MLDL models are becoming very large. So that is leading to this problem called out-of-code training. Okay, so that means you cannot put it into a single CPU memory or a GPU memory. So I need distributed training. And this is where if I want to go either like a scale up or scale out, there is no other middleware than MPI which provides that. So why not take advantage of that? And here, if you take a look, this is like on TAC Frontera. That is the Texas Advanced Computing Center. It's a very CPU-based DL training. Okay, if you have access to very large scale, you don't have to even depend on GPUs. You can actually use CPU-based training. Here, if you see, almost on a 512 nodes, we give like a 481x improvement. This is on the GPU-based training. We had this paper at SC 2020, and up to 1,000 GPUs. Here you can see we are able to scale very well. Okay, so we are trying to bring that MPI, the benefits of the MPI library now to the deep learning training. Same thing we have done for QML. That is a common framework which is being used for machine learning, not the deep learning. So what we have done is like through MPI for Pi, we have linked to our MAPs to GPU Direct RDMA library and see the benefits. So here we are comparing our MAPs to GDR with Nickel library, that is from NVIDIA. But instead of like a Nickel, if you use the MAPs to GDR, you see here almost like a 1.8x, 1.6x kind of improvement. Okay, so the story is same. Like since MPI provides the scalability, we are able to go to the next level. So then the third part, I'll try to show you the big data side, what is happening. So some of you might be familiar with this project. We have been running HighBD, this like almost 10 years. We started with Hadoop, Spark, those kind of stacks, and we really took it to the InfiniBand verse layer. We totally redesigned. Instead of using the Apache version of your Hadoop or Apache Spark, we took it to the InfiniBand. So these are a lot of things are already available. People have been using it. But recently what is happening is since a lot of these different networks have come, let's say Omnipath has come, the Slingshot has come. Now the challenge is whether do we do redesign again or we use our MPI library as a substrate. Okay? Because if we do the MPI library as a substrate, then automatically we'll be putting the performance to these different networks. So that is the very latest work what we have done. It's called MPI for Spark. Okay, so these are like the Spark things. If you take a look, one of the component is Netty. So we have linked that to MPI Java bindings, Java Netty module, and then the native MPI communication. And these, by the way, these are all publicly available. You can download, and here if you see, these are all InfiniBand systems. This is a Omnipath system. So we had two choices. Either we redesign our stack for Omnipath, or rather use our MapIs library, which provides both support for InfiniBand and Omnipath, and directly use that. Okay, and that's what you see here, compared to in Vanilla Spark or RDMA Spark, which was there. Compared to our RDMA Spark also, you see the benefit. Because RDMA Spark is a little bit older code base, so as the, let's say, InfiniBand is providing more and more features, the latest MPI library is able to take advantage of that. Okay, so that's how we are able to get the benefits. And here, especially for the Omnipath network, you see, RDMA Spark was not there. So instead of us redesigning, we just put it on top of MPI. And we have our MapIs running with Omnipath for many years, and now the Spark can run on top of it without any effort. Okay? So that's how we are able to move to this converged middleware stack. And then last we have done is the Dask. How many of you know about Dask or using Dask? Okay, so that is a new data science application domain is coming. So same thing here we have done, like a MPI for Dask. We have linked to MPI for Pi. We have linked to MapIs 2, both for CPU and GPU side. So here if you see, like take a look at the CUDF merge benchmark, which is a very common one in the Dask. This is actually running in Cambridge Wilkes 3 system. And here we see like so far prior to that, either you can run Dask with TCP or you can run Dask with UCX. But now compared to both, if you see these red bars, we can even give you 5x faster than UCX support. And right hand side you see you can give almost like a factor of 8 or 7 benefits in terms of throughput. This is the similar story matrix.benchmark, and this is also for the CPU. Okay, so in fact we gave just last week NVIDIA GTC happened, so we had a talk there. If some of you have registered, you can actually listen to the entire talk. We went into the very detailed design there. So with this, let me go into the last 15 minutes, focus on the final part. You remember the emerging computing continuum we talked about? So these are the new activities we have just started. And by the way, this is what I'll show in this part. I'm still the lead, but a lot of other people are working. Okay, so I bring their results, so these are not everything from my group, but from this institute. I'll try to show first the R&D focus, and then especially show two kinds of solution, like what we have done for digital agriculture and smart food set so far. So this is that computing continuum I indicated. So this is if those of you are familiar, US National Science Foundation is investing quite a lot on AI for the last few years. So we got this award, 2021, November we started. So we have just finished 1.5 years. So it is a $20 million grant. And the focus, this icicle is intelligent cyber infrastructure with computational learning in the environment. It's a very long word, but I'll try to answer this. So we have a very nice video here, and I'll play it. We may need to adjust the audio. Let's see.
A policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield. while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter Icicle, intelligent cyber infrastructure with computational learning in the environment. Icicle is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. Icicle will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The Icicle conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, Icicle would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. Icicle will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, Icicle produces a symphonic answer that improves outcomes for diverse stakeholders. Icicle holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
So I hope that gave you a very broad perspective. This is where the mandate from NSF is to really design this kind of cyber infrastructure which can be deployed in, let's say, 2030, 2035 onwards. And of course, the focus is like democratize AI. We want to make it so simple so that the end users can use it, okay? Think of like that digital agriculture example I said. Can we actually put everything together into an app and then give it to the farmer, like a $9.99 per month service, okay? So the farmer doesn't have to really learn AI or anything, just talk to the iPhone, saying, should I harvest today? What should I be spraying pesticides? And everything happens behind the scene. That is the kind of the goal what we have. And this is kind of the computing continuum I said. I have been talking about this digital agriculture. We also have two other verticals, animal ecology and smart food set. So smart food set is basically, think of like the disruption happens when some hurricane comes or some wildfire comes, how the food distribution needs to be remained consistent. And we saw that especially in the COVID days. If you remember, at least in US, a lot of farmers were dumping their crops because there was no way to move them. On the other hand, at a lot of places, people were standing for food. So this is the kind of the gap we want to bridge. And then once we have that kind of a solution, we expect like those can be replicated into all these other verticals. So as I said, this is a very big grant we have. OSU is the overall lead. I am the overall PI, but there are a lot of other universities here. I'll not go into details. So the way we are trying to solve this is through abstraction. So think of like the left-hand side, which is all the heterogeneity, and the right-hand side, these are the kind of the plug-and-play architecture we are trying to build. And also, there's a lot of focus on co-designing in our team. As I said earlier, like 46 PIs, there are 50 students, almost 100 people are working, and many of them are non-computer scientists. We have actually faculty from Department of Agriculture, faculty from food distributions. So we have been working with their staffs and students to come up with the solutions. So these are some of the lower level challenges, like how do you build very large scale knowledge graphs? How do you build model commons, adaptive AI, federated learning, etc. Then CI for AI. This is where like our HPC mostly comes in. How do I do high performance training? How do I do high performance data management? How do we provide adaptive intelligence over this different network? And then this is also interesting through these, because you remember in the title we say learning through computational learning in the environment. So this is the new field which is coming here called AI for CI. Okay, so how we can actually utilize current machines, how they are being used to actually design the next generation machines. Okay, so think of like schedulers. I'm sure all of you are familiar here. There are so many scheduling algorithms are there. Now, based on how the scheduling is happening these days, can we use that data to develop a model so that the next time a job gets launched, we don't have to go back to the algorithm. We just use our model as an inference engine, and then we say how to proceed. So this is the kind of the newer directions we are going. Of course, there is a lot of focus on privacy, accountability, data integrity here, visual analytics, explainability. And then, of course, the complete focus is on the software, how we can put it together here. So these are all our mandates. So let me show you how much progress we have done. Like putting together like a 100-member team, it took some time. But think of like a digital agriculture. Okay, so these are very clear things what we have done so far. Think of the left-hand side. These are how I am sure all of you would have seen in your garden or some places, diseases have happened. So a lot of agricultural faculty and students are actually developing AI models. So from this picture, can I actually show what disease happened here, what disease happened here? The right-hand side, let's say robots want to pick up apples. Just from picture, can I actually determine that the apple is right for harvesting? So those are all the machine learning models we are trying to use. And if you have that, then what you could do is there is a small video here. Let me play. It doesn't have the sound. So you can actually fly drones. And what we are trying to do, not only one drone, think of like a parallel processing across drones. If you have a very big field, you can actually, these actual experiments taken in the in state of Ohio, one of my colleague, Professor Chris Schwartz and his students are doing. You can actually, all these drones talk to each other, just like our parallel processing HPC environment works, and divide that land and actually come up with this kind of a heat model very quickly, saying what disease happened where, and that information can be fed back to the tractors or to the sprayer, and we have developed actually the Kubernetes-based this cloud to edge infrastructure, okay? So that you create the loop starting from the drone to the sprayer, okay? And real time you actually want to do this, and recently we expanded even this to between US and India. Is a supplemental grant because the digital agriculture is common all over the world, and the similar challenges exist, but the crops might be different. Like in US it is soybean and wheat, might be in the India it is potato and onion. Can actually you do transfer learning across these domains and have the similar kind of solutions? And then this is the final demo I want to show.
In this demo, Nancy, a land manager at a local open space district in Northern California, is concerned about wildfires on their properties. She wants to reach out to local livestock producers to both reduce fuel loads and provide forage opportunities for animal They use Peapod Knowledge Graph to help identify potential partners for their management needs. First, Nancy begins her quest by searching for her organization in the Knowledge Graph. She then clicked on her organization to surface the many relations visible via graph edges in order to find all of the potential partners within her eco-region. Nancy recently read about how grazing animals reduce brush limbs and the concomitant risk of wildfires, not knowing where her project partners may exist. She brushed all nodes to show detailed information in the table. From the table, she identified a potential project partner, California Grazing Land Coalition. Next, we used a data-driven approach to estimating high-resolution cold chain food flows between the counties and the U.S. based on national commodity flow surveys. First, we select the top 5 outflow degree counties. As you can see, the Imperial County in California has the most outflow for cold chain products in the U.S. Second, choose the top 1 and expand its connected counties on the map and show the resilience, which demonstrates the changes to the food supply of the cold chain mass transportation. Brush all the nodes to show the resilience on the map, which demonstrates the changes to the food supply of the cold chain mass transportation. Last but not least, we can further filter the most/least resilient nodes and shows its geographic distributions, which shows the potential issues in attacking us cold chain supply.
So this is the kind of the thing, what you can see, like, hey, we are trying to bring knowledge graphs, model commons, databases, combined together into building this entire system, and this is where the Icicle is heading. Of course, if any one of you are interested in collaborating with us, please take a look. These are all the links, whatever are available there. So with this, let me conclude what I indicated here, like the next generation exactly systems and cloud, you need to be designed in a holistic manner, like taking HPC, big data, machine learning, data science, and computing continuum, and I gave some examples. This is like a self-promotion I'm doing here. A lot of work what we have done in the big data computing has actually come out as a high-performance big data computing book by MIT Press. If you are teaching or you want to learn more about that, please feel free to take a look. With this, I'd like to thank all our sponsors. What I try to present here is like a 22 years of work, but last but not least, these are all my heroes. All of them have contributed to this work. So with this, I'll stop here. I know it's exactly coffee break time. And I'll be here today, throughout the today and tomorrow. So I'll be very happy to talk with you. Thank you.
Pam